Hi, I'm Amy Bodette from the Alt Store. Thank you for watching the last of our video series on designing an off-grid system. For this final video, we'll select the inverter for our off-grid solar system. Our previous videos helped us determine how much power we needed to make, what size battery bank was needed to store it, and what solar panels were needed to generate that power, and what charge controller is needed to manage the power. Now we'll choose the inverter. We're getting closer to completing the system. We figured out the loads, the batteries, the panels, the charge controllers, and the final components, the inverter. I did another video discussing the different types of inverters that you can go see. We're just going to do a brief reminder of an off-grid inverter's role. The primary job of an inverter is to convert the DC, or direct current, power from the battery bank, as seen in the red line, to AC, or alternating current power, needed for most appliances. To do that, it must take the constant DC voltage and change it to a sine wave curve that goes above and below 0 volts. When inverters first came out, the most common way to do this was to make the voltage go straight up and down, creating a blocky signal. This is called a modified sine wave. More advanced modified sine waves make multiple steps, trying to get as close as possible to a pure sine wave. You can see the output of a modified sine wave on an oscilloscope to the bottom left. It is an approximation of a pure sine wave shown on the right. So other than how the signal looks, what's the difference between the two outputs? A modified sine wave inverter can be used for simple systems that don't have any delicate electronics or audio equipment that may pick up choppy wave and produce a hum. Tube TVs and motors with brushers are usually fine with modified sine wave. But your digital clock will likely act funky, and battery rechargers quite often just plain old won't work. Some equipment might seem to be working fine, but it may run hotter than with a pure sine wave and reduce the life of it. It's very difficult to say exactly what will and won't work with modified sine wave inverters. Pure sine wave is always needed for grid-tied system. It is generally needed for the newer LED TVs, CFL and LED light bulbs, and inductive loads like brushless motors. Generally, modified sine wave inverters are less expensive than a pure sine wave inverter, so they are still commonly used in simple systems. But as technology advances, the cost of pure sine wave inverters is coming down, making them much more affordable and really the favorite option these days. With an off-grid inverter, these are used for standalone systems where the grid is not available. Once the charge controllers charge up your battery bank, the off-grid inverter converts the 12, 24, or 48 volt battery bank to AC voltage. The AC output depends on your requirements. In North America, you can use 120 volt single phase, 240 volt split phase, 208 or 480 volt three-phase, etc. Depending on how you wire the output of the inverter and which inverter you get, you could have both 120 and 240 volts as the output. You need to determine what your loads require and select and configure the inverter accordingly. An off-grid inverter cannot sell extra power back to the grid. However, an inverter charger can connect to the grid if available to act as a battery charger. For instance, if you have a boat or an RV with an inverter charger, when you connect to shore power, you can use the grid to charge your battery bank when the solar doesn't provide enough power. But that AC connection is one directional. It will only take power from the grid, not send it back. Likewise, you can often connect a generator to the AC input of an inverter charger to top off the batteries when needed. This is a common configuration for off-grid homes that need more power in the winter than the sun can provide. When selecting an inverter, you must determine what your maximum wattage draw will be if all your appliances that may be on at the same time are on. If you have an 800 watt well pump, a 100 watt fridge, 5 10 watt lights, and a 50 watt laptop, you'll need to add the wattages together to get at least a 1000 watt inverter. You also have to make sure the inverter is able to handle the surge as motors turn on. For example, if your fridge and well pump both turned on at once, the surge could be 3 times the rated wattage. You must make sure the inverter can handle that. Inverters are rated in both the continuous wattage and the surge capability. Additionally, you need to select the battery bank size and buy the inverter to match. Inverter voltage is not field selectable. They are either 12 volt, 24 volt, or 48 volt. They cannot do all of them, just one. Battery-based inverters have a lot of options to choose from. Not all of the inverters have all of the same features, so you need to decide which features are required and select the inverter based on which has them. Some of the features are the ability to charge a battery bank from an AC source like the grid or a generator, even automatically starting the generator when the batteries are low and turning it off when they are charged. Some can automatically use the generator to assist with high loads. Since the inverter is often installed in an out-of-the-way location near the batteries, a remote control or display in the living area is useful to keep an eye on the system. Some inverters even have the ability to monitor the system remotely via the web. This is very useful for part-time locations that you're not always there to keep an eye on it. Many inverters can be stacked to increase either the voltage or the current, or both. This allows you to use multiple inverters in a master-slave configuration, automatically turning on only the inverters as needed, conserving battery power. To size the inverter, let's add up all the devices that may be on at once and add up the surges. Inverters should handle 13 plus 30 plus 375 plus 1400 plus 120 watts, 1938 watts continuously. Note that we didn't include the DC lights, as they will be running directly off the batteries and not through the inverter. When we add up the surges that may come on at once, 13 plus 30 plus 1500 plus 4200 plus 1100 equals 6,843 watts. That's 3 times higher than the continuous wattage. So we need to find an inverter that can handle that big of a surge. As you can see, sizing an off-grid system is a delicate balance. When selecting an inverter, there are several key factors to look for. I've discussed many of them in previous videos. Looking at this data sheet of a Magnum Energy PAE series inverter, we can compare the MS4024 PAE and the MS4448 PAE. First thing to look at is the input DC voltage. The 4024 connects to a 24 volt battery bank, and you can see the input voltage range is 18 volts to 34 volts. Whereas the 4448 is a 48 volt battery bank. Its voltage range is 36 to 64 volts. Both of these models are able to output split phase 120 and 240 volts at 60 Hertz. So these can be used in North America with regular household appliances, in with larger appliances that uses 240 volts, like a well pump. You can see here that the 4024 can handle a continuous load of 4,000 watts, and the 4448 can handle 4,400 watts. So both of them are able to handle our continuous loads of 1938 watts. But now let's look at the surge ratings we were talking about. We calculated that we needed to be able to handle a surge of up to 6843 watts. The 4024 can handle 5,800 watts for up to 5 seconds, but the 4448 can handle up to 8,500 watts. That will allow us to handle our 6843 watt surge. So I'm picking the 48 volt MS4448 PAE for my inverter. Now we've done all the major components in an off-grid system except for one, the overcurrent protection or breakers. I did another video series where I went into more details of the breakers. For this one, I'm just going to do a quick sizing of them. There are 4 main segments that will require breakers: between the panels and charge controller, both in the combiner box and in the DC load center, between the charge controller and the battery, between the battery and the inverter, and between the inverter and the AC loads. Between the panels and the charge controller, each string uses the math of the short circuit current, or ISC, times 1.25 for NEC's 3-hour continuous, times 1.25 for over a radiance. The combined strings use ISC times 1.25 times 1.25 times the number of strings. Between the charge controller and the battery, use the charge controller's rating times 1.25. Between the inverter and the battery, use the rated wattage of the inverter divided by the lowest operating battery voltage times 1.25. And finally, on the AC side, between the inverter and the AC loads, use the rated wattage of the inverter divided by the AC voltage times 1.25. There you go. Well, now we can celebrate that we've done the major design work. There are still other things like wire sizing and racking. We've got other videos that go over some of that, but this should get you well on your way to designing your off-grid system. Check out our website for a selection of all the pieces you need for your system, including the inverters. Also watch more of our videos on our website. We've got a team of highly trained technical sales reps available to help you plan your system. Give us a call. Thanks, and don't forget to check out the rest of our site at altstore.com, where we are making renewable doable.